Hello everyone, welcome to the continuation session on logistic regression. Right. So before we actually go in detail understanding what is the hypothesis function of logistic regression, what is the cost function of logistic regression, right? So we'll just have a look at how logistic regression actually differs with respect to your linear regression, right? Because there are few similarities between your linear regression and your logistic regression, right? Looking at this image, right? So what you basically see is say this is your inputs. So your inputs are three variables, x1, x2, and x3, right? So each variable have its own weight. This is your intercept term, right? So until now, what you basically get is linear regression. This is what linear regression is, right? So you basically have inputs, say your w0 plus w1 x1 plus w2 x2 plus w3 x3, right? So you basically use any optimization algorithm like gradient descent to sort of find out the best possible values of your weights under the condition that you're basically trying to find the minimum of your cost function, right? So this is what basically is linear regression. But coming to logistic regression, even though this component is similar, right? What you basically see a difference is you basically have your sigmoid function, right? Sigmoid function is nothing but 1 by 1 plus e power of minus x. So that is what is basically a sigmoid function. So what basically the role of sigmoid function over here is to basically convert the whole of this into a probability, right? Either probability of either 0 or 1. So whatever output we get from logistic regression, right? So it's basically a probability of either 0 or it's probability of 1. So it's either between these two. Okay. So this is what is the flow of logistic regression, right? So you have your inputs, you have your W1, W1, W3. Finally, you pass that value to your sigmoid function. That's why you basically group logistic regression under linear algorithms, right? So you basically have a linear form factor over here, but over here, in order to get your probability outputs, you pass it through a sigmoid function. Okay. Yeah. So moving on. So this is what is the cost function for logistic regression. So as previously discussed, here the cost function is cross entropy or log loss. Both of them mean the same thing. So this is when your this thing is 1. So if your y value is 1, this is what the cost function turns out to. So if your y value is 0, this is what the cost function turns out to. Okay. So this is what is log loss. Very straightforward. Okay. So moving on, right? So next is coming to your hypothesis function. Okay. So what basically is your hypothesis function is basically this. Say if h theta of x, right? So this is basically a hypothesis function. So over here, say if I just represent this whole thing as z, right? So this is what is that linear form factor which we were discussing in the previous sheet, right? So now you basically have g of z is equal to 1 by e power minus z. This basically, right? This is what is your sigmoid function, right? So whatever linear form factor you have, you're just passing it to your sigmoid function, right? So this is basically your hypothesis function. Before we actually go on to looking at how do you calculate the derivative for cost function, all of that, we'll basically have a look at how do you calculate the derivative of sigmoid function, right? Because in your normal optimization or gradient descent step, right, calculating partial derivatives is one of the most sort of important steps over there. Before I actually proceed to that, we'll actually look at how do you actually calculate the derivative of your sigmoid function. Sigmoid is nothing but 1 by 1 plus e power minus x, right? So in this, we're just taking direct derivative, no partial derivatives over here, right? So it's d by dou x of your sigmoid. So this is the form 1 by x, right? So 1 by x is nothing but x power of minus 1. So x power of minus 1 is nothing but x power of minus 1 is nothing but minus 1 by 1 divided by 1 divided by x power of 2. Right, so that is what this is. So this is this into e power of x is minus 1. So minus and minus gets cancelled out. Next you're stuck with d by dx into 1 power of e power of minus x, right? Because you're assuming this as x power of minus 1, right? Then derivative 1 with respect to x is 0. E power of x is e power of minus x. Derivative of minus x is minus 1, right? So you basically finally you end up with s power of s of x into 1 minus s of x. Okay. So this is what is your derivative of your cost function. Right? So this is what basically is your gradient descent step. Right? Just to give a brief recap, right? So we had discussed this in detail in the previous session on gradient descent. Obviously, that was applicable only to linear regression, but over here just to give a brief recap, right? So this is what is the general form of gradient descent, right? So what is basically happening in gradient descent is, say to get one update, right? You're just taking the previous value multiplied by your learning rate, right? And getting the partial derivative of your cost function, right? Why learning rate is basically used? Because what we saw in, like we saw in the previous discussion on gradient descent, right? What is happening is if we actually run algorithm without gradient descent, what is actually happening was you're taking actually large update steps. With large update step, there is always a possibility that you will miss your minima. Right? So since gradient descent being an iterative process, after you miss your minima, right? So you'll get into this sort of loop where reaching minima would be an issue. Right? Now we have to make sure that you take small steps, but you do not overshoot the gradient. You do not overshoot the minimum. What you basically do is multiply by a learning rate. Right? This is what is gradient descent for general form. This is what general form of gradient descent is. Right? So coming to logistic regression. Right? So this is gradient descent applied to logistic regression only. Right? So in this, basically, what is happening over here is so your theta remains the same. So this is your new value. This is the updated value. This is old value minus alpha by m into h theta of y into x. So how do you get this? Is basically you get this after taking partial derivatives. After taking your partial derivatives, this is how you get this. Yeah, right. So h theta of this thing is your predicted value minus this is your actual value into your input. Right? And j is for each input. Right? So suppose in the initial sheet we saw you have 3 inputs, like x1, x2, and x6. So this is what happens. So that is why you have I is equal to 1. So this is for each of your input. This is what the formula is: predicted minus actual into your original value. So this is what is logistic regression gradient descent. This is what the derivative will turn out to. So we'll have even more detailed discussion on this through code. But before we actually jump into code, right, it would be very helpful. We can actually get a conceptual understanding. Code definitely helps. Code sort of solidifies your understanding of the concept. But having at least the initial conceptual idea of how it works would always be helpful, right? Just to reiterate what we have learned till now, right? Just to reiterate what we have learned till now for logistic regression. This basically is your cost function for logistic regression. And right until now, what we are looking at is we are basically looking at in parts. What will happen when y is equal to 1? What will happen when y is equal to 0? So basically, what I've done over here is I've just put everything into a single equation. Right? This is j theta. J theta is basically your cost function. So minus 1 by m yi into log of h theta of xi plus 1 minus yi into log of h theta of 1 minus h theta of xi. Now basically what would happen is, say if y is equal to 1, when y is equal to 1, this thing becomes 0. Right? So this thing becomes 0 and this thing goes away. Right? Now when y is equal to 0, this thing becomes 0 and this thing would go away, you would end up with remaining this. So the output wise is not much of a change, right? But what we have done over here is we've just put everything into a single line. So this is what is your gradient descent. What you're basically trying to do, you're trying to basically minimize your cost function, right? Theta of j minus alpha of, right, your predicted minus actual. After you subtract it, then you multiply it basically by the input. Okay, so this is what is gradient descent. This is what is the general form for gradient descent. Obviously, this is an iterative process. You will keep on repeating this until you basically reach your convergence. So right over here, what is your h theta of x is nothing but your sigmoid, right? If you remember in the beginning sheet we just saw, right, you have multiple inputs, right? You have 3 inputs. What you basically pass it through a sigmoid function, right? And whatever output you get is a probability value, probability between 0 and 1. Okay. So this is what is a overview of, at least a conceptual overview of logistic regression. Obviously, we will have a detailed walkthrough through the code as well, to make sure the understanding is clear. Okay, then so we'll meet when we'll have a detailed walkthrough through code. Thank you.